Welcome to ExplainerCast, episode 16. I'm your host, Dave Smith.
And this is Shane Swenson.
Today we're talking about GPTs, or Generative Pre-trained Transformers, the most popular of which is called ChatGPT. And we're going to explain how these things came to be and how they work to a certain extent.
Yeah, and this is really where AI has shown up in modern life. So this will be cool.
For sure. And I want to just throw back like 20-ish years, maybe 25 years when I was in college, and I was in the computer science program. And there were probably a good 3 or 4 professors who were specializing in artificial intelligence and machine learning. And they just had nothing to show for their work back then. I remember sometimes I made fun of it a little bit because I thought, this is just a bunch of math on chalkboards and these computers can't do anything interesting. Like you give it a picture, it can't identify a dog. You try to put it on a car and it can't drive more than 20 yards before it drives off the road. You know, that was the state of artificial intelligence back then. And I thought, this is going nowhere. Yeah. And fast forward 10 years, maybe 15 years, and we've had a couple of big artificial intelligence machine learning surges. And now these machines can talk to us in ways that just absolutely blow our minds and drive cars.
Yeah, absolutely. And I had the exact same experience. I think the AI hype that had started way back in 1950s, 1960s, and just really wasn't working. And at the time, the promising techniques were all about trying to encode human knowledge and human decision making into reasoning systems. And those just always seemed to fall flat. And you just couldn't bring enough computer memory and storage to solve the problem just through raw data. And I think the big change that we're experiencing is now computing systems are essentially massive and cheap enough that they can just crunch all the data and then they can find the patterns. And so we humans don't have to tell them what the patterns are. We just give enough data and then the patterns are discovered. And this technique is called deep learning, where the model is, and we'll define some of these terms, where the AI system, I'll say, is essentially statistically analyzing patterns in data and producing its own results. And this has enabled huge advances in image recognition, speech recognition, and now lately in the generation of data, like image generation and text generation. And of course, today we'll talk about text in particular.
Yeah, exactly. And some other time, we promise we will do a saga of episodes on the history of artificial intelligence and machine learning, and then deep dives into how those things work. But today, we're going to narrowly focus on GPT.
Yeah.
And this, like we said a minute ago, this came to the world just within the last 2 years in the form of ChatGPT.
Yep.
Actually, just a year and a half even, maybe less, where the world really became cognizant of it. And this, like Shane was saying, is kind of a new form of, at least new in terms of application, a form of machine learning, which is generative artificial intelligence, meaning that instead of you giving it like a picture and having it tell you, oh, there's a dog in the picture, instead you give it the word dog and it gives you a picture.
Right.
That's what generative means in the GPT. And then pre-trained transformer, we're going to go into that a little bit more. But Shane, first, you used the term model.
Yeah.
And I think we're going to use that term so much in the next few minutes that we should probably take a minute and define that.
Yeah, we should. Do you want to do it or do you want me to try?
No, I think you should.
Okay. Well, I'll take a stab and then you can help me fix it. So,
okay, we'll try.
Yeah, so all of these systems are going to have a way of receiving an input and computing an output. And like Dave said, it might be a discriminative model where often you give it the input and you want to know something about it, like, is there an animal in this picture or what's in it? Or a generative model where we'll give it a prompt and we'll expect it to produce a result, which might be text, it might be audio, it might be images, etc. And the computer system that takes that input and produces that output is commonly called a model because it is essentially a mathematical representation of the function that we're trying to have it perform. And in machine learning, we'll be defining the architecture or the structure of the model as machine learning or computer science practitioners, but the actual details of the math that takes place in the model and the exact numbers that are used are going to be derived by training that model, which is a process of presenting it with data and essentially correcting or telling it what its output should be. and then doing that over and over and over again, making small updates to those internal numeric functions until they generally produce the answers we like. And then we say that that model has learned the task and is now able to perform that task or that function on, on data in the future. So the collection of those numbers is called the model weights, or they're called the model weights, which are all the parameters that are used essentially to multiply and add to say what bits of information are most important in order to produce the right result.
Yeah, very interesting. And what makes machine learning different from just machine programs is that this model, this set of weights and functions, is really kind of a giant black box that is generally hard to understand what's going on inside there.
Yeah.
Whereas a traditional computer program that attempts to do the same job, you would have lines of code that were all written by a person and debugged and whatnot. But these models consist instead of all machine-generated, I'll just use the word code because I think in essence that's what it is.
Yeah.
It's just not like the kind of programming language code that we're used to seeing for computer programs. And so like Shane, like you were saying, these models traditionally for these discriminatory or sometimes called classic machine learning models or classifying machine learning models, you would give a system like thousands of pictures of dogs and then thousands of pictures that aren't dogs. And you would tell it, these are dogs, these aren't. Now go train a model that can recognize the difference.
Yep.
And be able, in the future, I can give it a new picture of a dog that it's never seen and it can come back and say, yes, dog.
Yep.
Or a new picture of something that's not a dog and it can come back and say, no dog. That's not what these GPT models are, right? They are not created by giving it a body of labeled data. By the way, the dog, no dog would be what we call labeled data.
Yep.
Instead, that's different. And maybe you could tell us a little bit about that.
Right. Yeah. And so, we call that supervised training or supervised learning, where we have a teacher, usually the human beings building the system, that are presenting the data and the answer key, essentially. And in the case of the GPTs and some of these other very large-scale models that are sometimes called foundation models, we're going to have a lot of jargon in this episode. We'll have to just pay that debt in the future by explaining all this. But for today's purposes, essentially the first thing we're going to do is just try to teach a computer system how to process the data, and not even necessarily what it means, but just sort of how to be able to distill it to a numeric representation that's more compact than the input, and then to sort of regenerate it on the other side. And there are a few different techniques for this, and it's often called unsupervised or self-supervised learning. So for example, for text, one task you might train the model on is to say, can you complete this sequence? So given a set of input words, can you then predict what the next word's going to be? And the nice thing about that is you just need text. You don't need humans to go curate this. You can just give them large quantities of text and work through it. Or missing words, like you delete a word in the middle and ask it to fill in the blank. And then similarly for images, you can do similar things. You can actually take an image and just cut a piece of it out and ask the model, fill in the gap, and then train it to fill in the gap effectively. And what this does, that task itself may not be that interesting, but it forces the model to develop an internal numeric and mathematical representation of like the underlying structure of the type of data you're feeding to it. And that ends up being the foundation for then building the different applications on top of that model. And that's why we call them foundation models.
Excellent. And Shane, you mentioned that one of the corpuses of data that we feed these systems to train these models is text.
Yeah.
But I also want to call out, it's not just any text. For these GPT models to be useful, you need to feed them text that actually looks like the kind of text you want the user to be able to interact with.
Yeah.
So it can't just be like a sequence of random letters and numbers. It has to be like the text of a book,
right,
or articles that you find online, or other natural language text that represents how users or humans actually speak. Because what it's learning is, okay, given the word the, what's the most common set of words that could follow the word the?
Mm-hmm.
And there's a whole bunch of words that can follow the word the, but there's a bunch of words that tend not to follow the.
Yep.
Like conjugated verbs, and it learns that, like, oh, you don't say the ran,
Yeah.
Like you wouldn't say that. You would say like the dog ran.
Yep.
It's like, okay. So it starts to discriminate those things and figure out where can words fit in.
Exactly.
And then the other thing I want to say on that was I think the main use case that motivated GPTs to actually get real engineering investment over the last 5 or so years was that it became very popular to help reduce the amount of typing input that users have to do on their phones and on Google search queries and things like that. And you may remember some years ago, maybe 10 years ago, Google would try to start predicting your next word in your search term.
Yes.
It's like you would say things and you get some really funny results with this,
Yep.
right? But like how do you, and then just like leave it and it'll give you 7 or 8 options.
Right.
And some of them are truly horrible.
Yes.
Like how do but what this is exactly why companies like Google and eventually OpenAI and others wanted to do this is because they could actually help you finish your emails, they could help you finish your search terms, they could help you finish your text messages,
Right.
and predict what are you most likely to want to say next.
Yep.
And that is probably the practical application that drove GPT development for text. And the specific kind of text models we're talking about here are called large language models, which is a specific kind of GPT.
Yes.
And this is what really took the world by storm over the last couple of years.
Yep. Yeah, and that's a great point that you want to feed it the type of input that's structured like you care about. And so this means it's human language. So written language, of course, has one kind of tone and construct to it, and that's a good place to learn grammar. But also person to person simple messages like Twitter messages and instant messages are also a really interesting source, because if you want the model to be able to communicate and interact, and especially to do predictive texting, then you need to know how people text. And people text very differently than they write books. And so these large language models are trained across a very large and diverse set of data inputs, generally representing human language, in order to learn all of the different kind of constructs and tones and so forth. And we should also say that another form of language that they can be trained on is computer languages. And so
yes,
maybe this episode or a future one, we can talk about the way that these language models are now able to interact with code as well as with human to human communications. And they're really quite effective at it because they've been trained on examples of code, including examples of code that were accompanied by commentary or questions and answers or explanations. And so there's some really powerful ways to leverage the interaction patterns across those different types of communication.
Yeah, it's actually quite amazing. It turns out, I can write a question like, how do I write a algorithm in JavaScript that will tell me if a number is even or odd?
Yep.
And it's like, no problem. This GPT model has been exposed to thousands of examples of that exact question, and so it knows now the most likely sequence of characters to output in the answer to that question.
Yeah. Yeah. So maybe let's talk a little more about training, and then let's move on to how these work and how we interact with them. So
Perfect.
The foundation part of this is a huge amount of training, which really means presentation of data and then an adjustment to the internal weights or parameters of the model so that it gives a slightly better answer, by some definition of better, next time, and then just repeating that over and over again. And these large language models use supercomputers worth of computation resource and internet scale data sets in order to build that foundational capability to distill the information from their input, whether it's text, image, or something else, and then to solve whatever the sort of the self-supervised task would be, whether it be to reproduce something similar or if it would be to fill in gaps that were cut out, are a couple of common examples. And the goal of this, again, is to produce a internal representation of the input that captures all the important details of that input that would enable you to then reproduce it and essentially interact with it in the future. And so there's another term we need to bring in here, and that's called an embedding. And we take our input, which might be maybe a paragraph of text, or it might be an image, and this pre-trained, largely self-supervised model will then take that input and it will compute this embedding, which is a sequence of numbers that represent the important information in that input. And the key here is that human beings, programmers didn't try to write that function and say, oh, I think that, we should take, these different properties of the data and we should make different measurements of them. The training of the model itself is what produces this embedding. And the cool thing is that these embeddings end up having a much more rich and detailed, what we call semantic level or meaning level understanding of what's in the data than any algorithms that computer programmers had built up to this point in history. And once we have that embedding, we can then now choose, well, what do we want to do with it? And maybe we want to reproduce the original data, or maybe we want to transform the data in some way. So maybe take, say, some input text and output it with in a different language or in a different tone, like say, take it from present tense to past tense, or take it from formal to informal. Or another very common one is, Dave, you were talking about predicting what words would come next. What if we ask it to predict entire sentences and paragraphs that should come next? And this is where ChatGPT really came into the fore, which was to make it interactive so that you essentially give it a prompt and then it returns back to you an answer.
Yes, exactly.
And so there's one more step in the training required to produce something like a ChatGPT, and that's where you take this kind of general pre-trained model, this generative pre-trained model, and we then refine it or fine-tune it for a particular task. And so, for example, there's a lot of different ways that you could follow a question with, what might come next. And some of them are more helpful than others. Some are more truthful than others. And so to build a model that does what we want it to do, which typically the models that have been built so far, the goal is to be truthful, to be helpful, to be kind, and so forth, then there have been, I guess I'll say, supervised training that are used to fine-tune these models. So this is where actual people will interact with the model and maybe give the model a prompt, like, what's the weather, what was the weather in California on a certain day of the year, and see what the answer that comes back is. And then of the different answers, maybe choose which one is best or which ones are acceptable. And then that becomes feedback to improve the model over time. And then this is how the actual chat-based models come out of these general transformer models.
So in this case, would you say that is it correct to say that the chat model is a fine-tuning of the foundational GPT model?
Yes. Yeah, exactly.
Very interesting. And just to give a sense for the amount of compute compute power and the sheer amount of electricity it takes to train these things, I want to say, I couldn't find a fact to back this up, but when Facebook generated their foundational model called Llama, I think it took them 30 to 60 days or something, running some hundreds or thousands of computers all at the same time. And it cost them over $2 million of electricity and compute costs to run that, just to get the foundational model built. So that kind of tells you the scale of power and cost these things take to create.
Yeah, they take a huge amount of data, and then, they take a huge amount of actual computation, which is why there aren't that many of them out there, and why we're not each building our own foundation model in our basement.
Right.
But we can gain access to them. Some of the producers of these give access through an interface where you can query and get responses from the model. Some have actually been open sourced and published, so you can download and fine tune it on your own and run it on your own. They do require even a lot of computation to execute, but not nearly as much as they took to train.
Yes. And interestingly, I believe they do execute and train on very similar hardware, which I think we talked about in our episode on, was it Moore's Law?
Yeah.
Where we talked about GPUs, or graphics processing units. Turns out they're very handy for large language model training and runtime.
Yeah. There's lots of small mathematical operations to perform, and GPUs are well suited to that. And at this point, the vendors building GPUs understand this is a key application. And so there's some alignment of the architecture of that processing unit to these machine learning workloads in addition to the original graphics workloads.
And then one more interesting thing to talk about is the coalescing of factors in our computing world that allowed these models to come to be that's kind of serendipitous, which is, number one, like you mentioned, Shane, in the 50s and 60s, we simply didn't have the compute power to generate anything like the large language models that we have today.
Yeah.
And we also didn't have the digital information recorded in such a way that even if we did have the compute power, man, I keep saying compute powder. Even if we didn't have the compute power, even if we did have the compute power, we wouldn't been able to train it on any data because we just didn't have everything digitized. And so it really has taken all these years to simultaneously develop compute hardware that can do these things, and also to collect enough digital information online to serve as a big enough training set for these models to actually be generated.
Yeah, exactly. Yeah, just even the transformation of human interactions into these digital spaces is part of what has produced the data sets, and then the ability to have enough storage, networking, and compute resources to process them. So it's probably something that in hindsight, you could predict exactly when it was going to happen, plus or minus 2 years, say, just based on the scaling of all of those factors. And that was just recent.
Yep, just barely happened. And you got to be here to see it.
Yeah, we all did. So let's talk just a little bit more about how these end up working in practice. So we said, okay, we did a bunch of training that essentially taught the model how to just sort of, I wouldn't say understand it. It's so easy to personify these things, and I'd prefer not to, but it's hard not to. But how to extract the relevant information from data they're presented with, and then how to produce outputs based on that relevant information that satisfy the customer, being, the users. And then those are tuned to a specific task, such as this is going to be an interactive chatbot. So an interactive chatbot is going to receive a question or a prompt, and then it's going to respond with its response. And so if you ask it to tell you a joke, you'd expect it to come back with a joke. And if you ask it to specify some piece of information, provided it has access to and have been trained on that information, you'd expect it to give you back a reasonable answer. If you ask it to derive something from text you provide as an input, you'd expect it to do that. And so,
like a summary, for example.
Yeah, exactly. Yeah, summarize this text or tell me the main point of this paragraph. Like, again, you would expect it to be able to do those things. So the question is, are these devices, are these algorithms or models, are they thinking? Are they reasoning? Are they performing logic? What are they really doing to provide these responses?
This was a question that got a lot of attention actually several years ago when GPT 3.5 came out, actually 2 years ago this month, where it produced such uncannily human-looking textual output that people started to wonder, maybe humans are just GPT models. Like maybe our
Right.
brains are just transformers that have looked at so much pattern-matched text that we can just answer from patterns.
Right.
And then and that, which was funny, is like, okay, well, are humans computers? Maybe. But then the other side of that question was, are computers turning into sentient, conscious beings?
Right.
That was a very, very common question as well. And I think you can answer that question pretty easily by looking at some of the questions that are very hard for these models to answer. For example, they can't really do arithmetic. If sometimes they get lucky. For example, if you ask a large language model what 1 + 1 is, it will almost definitely have the correct answer.
Yeah.
And that's just because it has seen so many instances of 1 + 1 being declared as equal to 2 that it just knows that's the most common text to follow 1 + 1. But if you give it more complicated math, it will usually get the wrong answer. Although in the GPT version 4, it's surprisingly good. And I think that's more of a feature of the huge amount of data that it has been trained on, that it actually has seen so many different examples of arithmetic and other like mathematical functions that it kind of starts to pattern match its way to glory, and answer these things right.
Right. And I think that's the key, you're getting to the key attribute, and that is that these really are pattern matching data analysis followed by data generation machines. They don't have inherent logic or reasoning built in yet. They're really just given this input, what's the most likely output that should follow it. And so they can do simple logic puzzles, including arithmetic, but when it's complex, then they'll typically fail. There was an interesting paper that showed that if the prompt included a specification that the model should take more care in generating the answer, or even better, should show its work step by step, that then the model actually performed better. And the way I think of that one is the way that these generative transformers work is their input is split into a sequence of individual elements, and then really their job is to say what should the next element following this sequence be. And once they've generated that next element, they now have a slightly longer sequence, and they just say again, what should the next element following that one be? And so they generate step by step by step the outputs. And so when they're told to show their work, they actually generate intermediate steps, which then inform the follow-on steps. And so sort of, it's like watching my kids learning slightly, learning how to solve like word problems in elementary school math. And if they just guess at the answer, they might get it 30% of the time. But if you ask them to show their work, now they might get it 70, 80, 90% of the time, because it forced them to be methodical. And so you can actually force these models to be methodical, but they're not using logic. They're just being methodical in the language and in the information contained in that language space. I do think there will be future architectures that, and I think people are working on trying to incorporate logic and reasoning and some of these other concepts more directly. And so we'll see where that leads. But for the current state, these are extremely sophisticated and very broadly based next word predictors. And it's crazy how effective that is at producing a useful thing.
I think we're all very surprised by that. And so much so that we sometimes refuse to admit that that's what they are.
Yeah. Yeah. They seem like so much more.
There must be more going on here.
Yeah.
Yeah. But this is why, for example, when you ask a large language model a question that it doesn't know the answer to because it wasn't trained on any data that actually contain that answer, it will invent one.
Yes. Which also tells you they weren't trained very much on people saying, I don't know. Like, I guess we don't say I don't know on the internet very often. We always assume we have an answer.
And, as I talk to people about this, they're like, wow, it's actually remarkably human. A lot of people do that too. It's like, I ask you a question and you say, well, here's the answer, but it's total crap.
Yep.
So it's like, well, I guess that is quite human.
Yeah, fake it till you make
it.
The
world has adopted a term for this, and they call this hallucinating, when a large language model makes something up like that. But, it's a fine term to use for this, but I actually think everything it does is a hallucination, because everything it does is just predicting what the next token is going to be in a sequence, given an input sequence.
Yeah.
And so it's all made up. Like, it's not like it's going to some internal database and checking some relationship. Like, okay, I've got an entry for the Eiffel Tower, and I know how many meters tall it is, so I can give you that. It doesn't really have that internally, or if it does, we can't tell. Because it's actually impossible to inspect the contents of these things.
Yeah, they're way too complex for easy analysis. People have built some tools that look for it's actually funny, kind of like how we do functional MRI on people's brains and look for what lights up. And people built some tools that look inside the parameter space of these models. And so we can say, oh, interesting, that area lit up with this type of prompt, but we really don't understand what's going on inside. I would say we should talk about a couple of things, because people will interact with these in a couple ways. So the model as built will often have I forget if there's a technical term for this, but sort of like an event horizon date where they were trained on data that was current up to a certain point in time. And so anything newer than that, they don't have a basis for how to answer if you asked for like a historical fact that occurred after that date. They just wouldn't have any input to even refer to. So it would for sure be just speculation. There is a type of architecture, and there'll be a lot of architectures coming out where people take these language models and don't just use their internal knowledge, but hook them up to other systems. And some of the search providers are now doing this. So both Google and Microsoft do this now, where you can have AI-assisted search. And in that case, the language model still has its sort of language understanding, if you will, built into it, the language manipulation capabilities, but has also been connected to essentially a conventional search engine where it can ask for a lookup, and then it can get the results of that lookup, process them through the language model, and format them maybe to be more of like a descriptive answer as opposed to simply a link and a summary. And so in that case, you have access to contemporaneous information through the linked search capability, and the language model is essentially your interface to that search, and then, the explainer of the results.
Exactly. And it works remarkably well because these language models are actually great at summarizing text and answering questions given an input of text. And so if you give them access to go to essentially give instructions to another, what they call agent, to go out and look at a web page and capture the text from that web page and then feed that back into the language model.
Yep.
The language model can now do things like give you source URLs for facts that it generates. Mm-hmm. And now they've become very, very valuable because in the early days when ChatGPT was just coming out, it really was quite dubious, I would say, in the results that it would produce because of this hallucination problem. Yeah. But now they've patched that by kind of supplementing the native large language model with this agent concept that allows it to go and gather more information and do what language models do best, which is given input text, summarize that text, answer questions from that text, pluck out information from that text. But they're not great at just self-referencing their own model and providing factual information.
Right. And to me, that's an exciting development because it always seemed kind of weird to try and just encode all knowledge into the embeddings in the model. That seemed like it was going to be a losing game. But teaching the model, instead building a model that is efficient with language and information processing, and then giving it access to authoritative information storage and retrieval systems, to me, that sounds like a very powerful and very generalizable architecture, because then you can also take that model and point it at other systems. And so I think over time, we'll find that these agent-based solutions end up becoming very common, and they're going to become just a common way we interact with our computers, our mobile devices, and like at work, I think about all the different documents that we create, and I really want one of these agents to help me interact with those documents and so forth as we go forward.
Yeah, they've been very, very good. Well, did we sufficiently explain GPTs?
I think we gave a good overview and probably created a whole set of potential topics to go into if we choose to do an AI saga at some point. So yeah, I think this was a good start.
Absolutely. Thanks so much, Shane. We had some explaining to do. We did some explaining. Thank you for listening.
All right. See you next time, Dave.